Okay. Number 48 on page 220. There is a set S. It has 4 polynomials there. 4 polynomials in P3, and we want to know if the set S spans P3. Okay, let me write set S here. Okay. 4 polynomials in there. Those are vectors in P3. But we want to know if this vector, if this set of 4 vectors span P3. How do we know? How do we know that S spans P3? Well, we can check if whether any polynomial in P3 can be written as a linear combination of those 4 polynomials. Okay, that's the idea. So we pick a general polynomial in P3. Okay, don't pick a specific polynomial. Pick a general polynomial. Okay. So in P3, it's a polynomial of degree 3 or less. So pick any vector in P3. So here it is. U. Okay, so U would be in P3. That means U is of this form. It's ux cubed plus bx squared plus cx plus d. Okay. Now we want to know if this vector here that we pick can be written as a linear combination of those 4 vectors. Well, let's set up the equation. Okay, here it is. Here's a linear combination of those 4 vectors, and we want to see if this U that we picked in P3 can be written as that linear combination. Okay, we need to find, we need to solve for C1, C2, C3, and C4. We're not solving for A, B, C, D. A, B, C, D are given numbers, okay? They're given. They could be anything. They could be any number. We're solving for the C's. Well, let's set up the system and then get a matrix and see what we can do with that matrix. Okay, how do we obtain the matrix? Well, you need to expand this whole thing here and collect the coefficients of each of the x, x squared, and x cubed, and the independent terms. Collect each one of them, and then you're going to set them equal to A, B, C, or D. Okay, let's see. Let's collect all the coefficients for x cubed. Okay, here is C2. There's no x cubed in here. Okay, here there's x cubed, so it will be C2 x cubed. Okay, here's all the coefficients of x cubed. C2 is one of them. And it's part of the coefficient of x3. Here's another one, C3. Okay, and there is no more coefficients for that is part of C of x cubed. Now let's collect all the coefficients for x squared. Here's one, C1. Let's see, any other coefficient for x squared. Here's another one, that will be C3 times negative 1. Okay. Here's another coefficient for x squared, it's C4. Alright, let's collect all the pieces for the coefficient of x, of just x. Okay, here's one, it's negative 2, but multiplied by C1. So negative 2C1. Let's see, here there's no x, there's x cubed, but we're collecting pieces for x, just x. There's no x in here, there's no x in here. So that's the only piece we found for x. Now let's collect all the independent terms. There's no independent term here. Here's one independent term, 8. So that will be 8C2. There's no independent term here. Here's one independent term, negative 4C4. Okay. And that is equal to this. Okay, let me copy that here. Oops. It didn't work fine here. Alright. Let's try again. Copy that and then paste it here. There we go. Okay, now I can set up my system. C2 plus C3 needs to be equal to A. right? So C2 plus C3 equals to A. Here, this coefficient needs to be equals to B, so that's C1 minus C3 plus C4 equals to B. Then this coefficient here, negative 2C1 equals to C. And then finally, the last coefficient, the independent term, equals to D. So that would be 8C2 minus 4C4 equals to D. Okay, so that's the system that we need to solve. Notice that these are not specific numbers, so it will be kind of hard to solve this in the calculator, right? So let me write the system here for you. Okay. Now, can we solve the system? Can we reduce this thing? You're welcome to reduce by hand, but I think we can solve this directly. So you look at the third row here. The third row is telling us that C1, well, we can actually solve this straight from here. We didn't have to put that in the matrix form. But we can see that C1 is C over negative 2. Okay, what else? Here, well, we're going to have to solve for the other variables. So here is C2 equals to A minus C3. Let's see if we can get C4 from here. C4 is B minus C1. See, C4 is B minus C1, and I know what C1 is. It's C over negative 2. So it's B minus C over negative 2, and then plus C3. And then the last row gives us C2. C2 equals to D plus C4, 4C4 divided by 8. Okay, we still need to find C3 here, right? So we can combine perhaps these two here. If we add these two, we can get rid of the C3. So C2 plus C4 equals to A plus B plus C over 2, right? C2 plus C4, A plus B, and then negative C3 with plus C3, they cancel, and then I have minus is positive C over 2. Okay, and then I can combine these two here to solve for C4. Kind of messy, right? Combine these two equations here. So I get, if I combine those two, I should get, that's what C4 is. C4 is A plus B plus C over 2 minus C2, so I put that in here. This way I can solve for C2. Alright, so here, C2, and then 4/8. This is 1/2, okay? So 1/2 times negative C2 is positive, it's negative 1/2. When I move to the other side, it's positive 1/2 of C2. So 8, 4 of 8. This is 1/2, I should have written 1/2. And then A plus B plus C over 2. Okay, so this term is going to the other side. It's 4/8 times negative C2, and then I move that to the other side. Okay, here's C2. This is 3/2. It's 3/2, but when I divide by 3/2, it becomes 2/3 on the other side. So D over 8 plus 4/8 A plus B plus C over 2. That's C2. Okay. And then, so with C2 you can get C4. And with C4 you can get, let's see, let's summarize this whole thing here. Okay, we can get C1. That's C over negative 2. What else we can get? Here we get C2, which is equal to this thing here. So when you copy and paste it here. Okay, let me squeeze a line here to separate that. How about C3? Well, if you look at this equation here, C3 is really A minus C2. So here we can find C1, here we find C2, and then once we find C2, C3 will be A minus that, whatever we found here. And then C4, C4 is found by this equation right in here. So let's copy that. Okay. So, there it is. Alright, we found C1, C2, and then once we find C2 we can get C3, and once we find C3 we can get C4. So those values can be found. So therefore, this was possible, okay? It was possible to solve for the C's. Therefore, any vector in P3 can be written as a linear combination of those 4 vectors. So we were able to find C1, C2, C3, C4. Therefore, any vector in P3 can be written as a linear combination of vectors in S. Okay, and that's the end of it. Now let me, you can stop here if you want, but see, this seems to be very confusing. You have to solve this by hand. Now let me show you one way you can use. It doesn't work every time, but it might work most of the time. And here is the idea. You can get this matrix here. Let's pick this matrix here for a moment. Okay. Since we like to work with these matrices, so let's pick these here. This one here. So let me put this down here. Okay. Now remember that this is actually a system, okay? And we can write this in the matrix format. We can write this as a matrix equation. So here's the coefficient matrix, and this will be the right hand side. So let's do that. Okay. So here are the variables. In the augmented system we don't see the variables, but in the matrix, so this is a matrix equation format. And I don't know if you remember this from the first course in linear algebra. This is the coefficient matrix. This is your matrix unknown matrix, and this is your right hand side, right? We're solving for x, the big X here. That's the variable matrix. Okay. To solve this, we can actually find the inverse of A. So the question is A invertible? It's invertible. Is A invertible? How do we know? Well, we can check the determinant. What is the determinant of A? If the determinant of A is 0, then A inverse does not exist. Right? If the determinant is different than 0, then the inverse exists. So the conclusion here, you will see that the determinant is not 0. You can compute that in a calculator if you want. Okay, here it is. The determinant is actually negative 24, so it's different than 0. So you can actually solve for those c's, right? So it means there's an inverse. And so the determinant of A is negative 24, which is different than 0. So A inverse exists. So the conclusion is we can find C1, C2, C3, and C4. We can solve for X, right? All I have to do is to write C1, C2, C3, C4 as A inverse times A, B, C, D. You can actually find the inverse in the calculator. Just type A to the negative 1, and that will give you the inverse, okay? And then multiply that inverse matrix with A, B, C, D, and then you will find formulas for C1, C2, C3, C4. Now, I mentioned that this sometimes, most of the time, works, but remember, if the matrix has an inverse, if A has an inverse, then you're fine, you're done. So we can solve for C1, C2, C3, C4. But if the determinant is 0, and therefore the inverse matrix does not exist, it doesn't mean that you cannot find C1, C2, C3, C4. You can still find them. The only problem is that you can't find by using inverses, okay, of matrices. So let me write that down here because it's important. So if the inverse exists, then we can find the scalars. But if A does not exist, don't assume that we cannot find the scalars. Maybe they don't exist. Maybe we cannot find them. But maybe we can. Maybe we still can't find them. So in this case, it worked. I mean, the coefficient matrix is invertible, and that means it's done. We are able to find the scalars. Okay, let's look at the big picture. Okay, what are we doing here? Okay, we have S. Okay, we have 4 vectors in S. We want to know if S spans at P3. How do we do that? Pick a vector in P3, a general vector, any vector in P3, and then see if we can write it as a linear combination of those 4 vectors in S. And then form a matrix, a system. Okay, you can try to solve it by hand. What I would do is to go check first if the coefficient matrix is invertible. If it's invertible, then you're done, right? We can find the coefficients. But if the matrix is not invertible, it does not mean we cannot find them. So we were able to find the coefficients, therefore S spans P3.